Okay, so in lesson 6.2, now that we know what vectors are, what a vector is, we're going to be looking at adding and subtracting of vectors, and we're talking about geometrically, okay? So some key ideas when we're looking at the addition of vectors, for all of the addition, all of this first page, and even I'm just taking a look for this, for the subtraction, my vector A is going to look like this the whole time, like the same direction, the same length, same magnitude, and vector B is going to look like this the whole way. So vectors can be added in various ways. So there's two ways that we're going to be looking at. One way is the head to tail method, or otherwise called the triangle law of addition, and the other is the tail to tail method. I'll show both ways, but basically the way that's most common after this and for when we're graphing is actually the second way, the tail to tail method. But I'll show you in the last example of this lesson how the head to tail method also works. So that's why it's good to know both. So the head to tail method. So if I have, just showing you here, let me just get my pen ready here. The head to tail method. So we know what a head is and a tail is on a vector, right? The tail is actually the beginning part, or the part that doesn't have anything at one endpoint, and the head is the other endpoint that actually has the arrow on it. So if I'm going to draw vector A, so we're looking at, I'm looking at these two vectors here, which one is vector A? So vector A would be at the bottom. I'll just label that. I've got my pen. Vector A. Okay, and then I've got vector B, which you can see here. This is the tail to the head, the arrow, and then I've got tail. This is an arrow here, so this is vector B. So now let's follow what the instructions are saying there. So I've got draw vector A. So again, I copied out vector A for you, exactly the same there in length and direction. Then draw vector B, but here's the catch. So that the tail of B, so the beginning of B, continues from the head of A. So basically, here's your starting point. You draw one vector, keep your pencil there. From that head, that end point of the one vector, you start the other vector and draw the other vector, and then that would be the end point or head of the second vector. Then the result of adding them, so in order to add them, what you do is you'll get a single vector when you add them together, and you start at the tail of vector A, so the tail is the beginning. So the beginning of vector A, just kind of pointing out there, to the head of B. So again, the tail is the beginning, the start of A, to the head of B. The head of B is the end point of B. So you just basically go from where you first started your diagram to where you ended your diagram, and you put an arrow at the end, right? So this here just pointing out is your resultant, and it's called the resultant. So the resultant is just the sum you get, the answer you get from adding two vectors together, and that's how the notation of it here is a capital R with the vector on top. So the resultant vector, because this is a vector as well, right? You get a single vector when you add them together, is equal to vector A plus vector B. So that one, the main thing is you go from tail to head, and from that head, you start the next vector tail to head. And then your resultant starts from the beginning tail to the ending head, from where you first started to where you ended the diagram. Okay, and let's compare that to the tail to tail method, which is the one I'm saying you'll probably be using the most. So again, draw vector A. So I just want to show you here, if you see vector A down here, it's the exactly same as this vector A, exactly the same as that vector A. So here's vector B at that type of angle, that type of length, which was here vector B, which if I bring it down is here vector B. You can see that that's all the same. So let's label it. So draw vector A. So here's vector A, right? This is the tail, which is the starting point. This is the head of vector A. Then draw vector B so that the tail, though, of B touches the tail of A, which is why it's called tail to tail. The two tails are together. So I'm going from tail to head, and then I'm drawing vector B, which is right here. But the tail, the beginning part of B, the tail, is going to start where the tail of A is and go in whatever opposite direction, whatever direction your second vector is, right? And this is, sorry, the head of B. So again, your two tails are put together. Now this is going to look like, see why it says it's the parallelogram law of addition? So then the second bullet here, when it says complete the parallelogram, these are two sides of the parallelogram, right? So then I would add dotted lines here to complete the parallelogram, and your corner should be right where, the head of the resultant is going to be. So then the resultant line, the single vector that you're going to draw, is going to start from where the tails of A and B are together. So it's going to start from, just putting it red here, it's going to start from where the two tails come together to the opposite vertex in the parallelogram. So just to the opposite corner. And again, you draw an arrow that's the head, so you know the direction of the resultant. And that again is a capital R with the vector symbol on top. So that's the resultant vector. So if I were to compare this resultant vector, just to move this up to, you see here, side by side, this resultant vector, I mean, the answers are going to be the same, right? I'm showing you two different ways of doing it. The answers are going to be the same. It's up to you which way you choose. Again, you'll see an example of how the head to tail method works better when I don't want to draw or need to draw a parallelogram. Otherwise, I would say that this method number 2 is probably the better one to use, especially when we're graphing. So now let's move on to subtracting vectors. So let me just clear this. So again, my vector A and vector B are the same, right? So just reiterating here, vector A and vector B. So the subtraction of vectors, what I actually do is add the opposite, right? So if I have vector A right here and I want to subtract vector B, which is right here, that's going to be equal to the same vector A, but I'm going to add to that the opposite vector B, the opposite of vector B. So I need to go write down what is the opposite of vector B. So the opposite of vector B, again, opposite is the same length, the same magnitude. So this is my head, so that's where my tail will start. And again, I'm drawing it parallel just best I can. And then here at the tip, putting an arrow for the head. And this would be then the negative of vector B, which is the opposite of vector B, right? Same length, parallel, just different direction. So then if we compare that to these two down here, right? So there's two ways that I can, again, subtract the vectors. So my head to tail method, or the triangle law of addition, the same as the first example in the addition, would be to draw my vector A. So again, vector A must be this vector here, right? And then my vector B, right, is this vector here. So what I'm doing, look, is I drew vector A, which is right here, but I'm adding to it. So if I'm adding, I'm starting at the head of A, and then I'm just drawing the opposite vector B, which is why it's going in this direction, right? So this is the negative B vector, the opposite B vector. And then the resultant is the same thing. From where you started your drawing, right here, to where you ended it. From the tail of the first vector A to the head of the second vector B, or in this case, the opposite of B. And this is your resulting vector, which I'll just kind of highlight here in red. Right, and again, put the arrow at the end, and this is my resulting vector of subtracting them. So this resultant vector is vector A adding the opposite of vector B. If I were to do this as the tail to tail method, again, you can see vector A would be vector A right here, vector A. So the tail to tail method is, again, I have tail, the beginning, to the head of vector A, and then I have vector B, but if I'm going to add the opposite, I have to use the negative vector B, the opposite vector B. Put the tails together. So this is the tail of the opposite vector touching the tail of vector A and drawing the opposite vector B. So that is the negative vector B. And then when I draw my resultant, right, my resultant starts from where the two tails, the corner where they come together, right here, to the opposite vertex corner. right? And I wouldn't know where this spot is here, this arrow, unless I complete my parallelogram. And I'm basically stopping where I'm looking visually at lining up to the tip of this, the head. And here again, how do I know when to stop is when I'm visually looking at where that would line up. And again, if this is my resultant vector of subtracting the two, this red line here and this red line here are exactly the same, right? Doesn't matter which way you do it, you're going to get the same answer, which is a single vector. Let's look at, just to explain to you what a zero vector is. So a vector with a zero magnitude, so zero length. So basically it doesn't exist, right? And no specific direction. So it is the result of adding two opposite vectors. So opposite, again, they are the same length already, they're just going in different directions, or subtracting two equivalent vectors. So if I have two equivalent vectors that are exactly the same length going in exactly the same direction, and if you just think about it, if I'm taking one and subtracting another, then taking one and subtracting one that's exactly the same length and exactly the same direction, obviously it's like getting rid of it, right? It would be have a zero magnitude and be a zero vector. I'm just going to try to move this over. I had it, there we go, perfect. Hopefully it stays like that. So here again, the zero vector would be like it says here, the result of adding opposite vectors. So vector v and adding the opposite of that, the opposite of vector v is going to equal the zero vector, or subtracting two equivalent vectors. So I have vector v and I subtract another vector v is going to give me the zero vector. So if we take a look at these vectors here, so let's say I have a vector v right here and I just make it a line like that with my tail and my head, and that's vector v. If I was going to add to that the opposite vector, so just to change the color here, if I was going to add to that an opposite vector v, so the opposite to it, right, is just going in the opposite direction. So putting the tail where the head is when you're adding, right, head to tail method, let's say, and then going in this direction and putting the head at this side, then you would see I can't draw a resultant vector, right? The resultant vector doesn't exist, so it's a zero vector there. So there's no resultant to draw. And if I were to do same, to draw my, just to draw out, well, I mean, it's right there, but just to show you then, that would be my negative vector v, the opposite vector to v. And same if I were to have vector v, there's vector v there in red. And if I was to subtract vector v, again, to subtract, you're adding the opposite anyways. So I'm doing the same thing as above, and I would get the same result, which is no resultant, and we just call that a zero vector. So looking at some properties of vectors, we have a vector u, v, and w, and we don't have a drawing because we're just talking in general here. You'll see what I mean. The commutative property, which we've looked at sometimes in the past, if I have a vector u now and I have a vector v and I'm adding them, does it matter if I take u plus v or vector v plus u? No. Same as 1 plus 2 is 3 and 2 plus 1 is 3, right? So that's just saying that the order doesn't matter. We should know that. The associative property is if I have a vector u plus vector v in brackets, where I have to add those together first and get a resultant, and then add vector w to that, I'll get the same answer as I would if I were to take vector v and vector w, add those together because of the brackets, and get a resultant, and then add that to vector u. It doesn't matter, again, when you're adding, if you add the first two together and then add the third, or add the second and third together and then add the first. Okay, and the identity property would mean if I have vector v, so same as up above that I just drew, if I have a vector v and I'm adding a zero vector to it, I'm adding nothing to it, well then that's just going to give me be equal to vector v, right? And that's the same thing as, or having a zero vector, nothing to start with, and then adding a vector v to a zero vector. I'm still going to be ending up with vector v. So that's the identity property. Whatever vector you have, adding a zero vector is just going to give you that vector itself, right? That seems pretty Pretty self-explanatory. Okay, let's do some examples here. I've got just two here. So given vector, if I look at vectors u, vector v, and vector w, draw each vector expression. So I have here A. 1A is I'm taking vector u and I'm going to add vector w, right? So if I'm adding them, let's redraw vector u, which was right here. Do I have my pen? Let's draw vector u. It's not very straight. I mean, I guess I can use a straight line, sure. Let's go up. Do I have an arrow one? So let's add, give me vector u. Perfect, looks much better than what I'm doing. And then if I want to add vector w to that, right, then if you see here, vector w here, vector w is going in an opposite direction. So if they're opposite vectors, not opposite meaning I know they're not the same length, but going in an opposite direction, then we can't use the tail to tail method here, okay? So using the head to tail method, I would have vector u, and then again, keep my pencil at the head of the first vector I drew. And then from there, I start drawing the tail of vector w to where the head would be. So again, if I change the color here, let's just say, and put, oops, do I have to pick? And then say that this is vector w, roughly, I'm just kind of guessing that it's that size there. So let's label what these are. So I have, again, vector u right here, and then I have in blue my vector w right here. So if I add them together, the resultant is, again, I'll do that in red, starting at the beginning of where I drew my first vector. So from here, again, I'll use an arrow here, to the head, to the end point of my second vector. So from here to here, right? That would be my, well, should be a little longer. That would be my resultant. So this is my resultant, this section here, okay? What if I had vector u minus vector w? So I'm doing the same thing, but I'm subtracting them. Well, how do I subtract them? How am I supposed to subtract them, right? Remember, I'm supposed to really take vector u and add the opposite of vector w. That says vector, sorry, vector u, and add the negative vector w. So again, I need to write out what the opposite vector w would be. So I'm going to start here. Actually, at the tip of where the head starts is where you start it, to the end. And when you get to the end, that's when you draw your head. So again, this is the negative w vector, the opposite vector to w. So if I write this out, we've got vector u. So let's write out vector u in green again then. Try to make it the same length. So vector u, I'm just looking up above and comparing, let's say roughly like that. And so this is vector u. And to that I'm adding, so again, I'm going to add the negative, the opposite of vector w. So where this head is, I'm starting the tail of my opposite vector. So I'm actually adding in length to it, right? And let's just go back to brown, make that brown. So I'm adding, now this is the head, so the tail is starting here of the opposite vector w, and I'm continuing on that small portion there, whatever length, probably a little shorter, I think. Wasn't supposed to be crooked. There's my negative opposite vector to w. And so then again, follow the resultant rules here. The resultant is I start at the beginning, the tail of my first vector, and I end at the end value, the end point, the head of the second vector. So I'm just going right from the left side all the way to the right side here. Right, and that is my resulting vector of technically subtracting the two of them together, or taking one vector and adding the opposite of another vector. Okay, let's try if I had 3 of them together. Vector u plus vector v plus vector w. So using all 3 from up above. So let's try my best here. Vector u was always green. So let's do the same thing. Draw. You guys draw vector u and roughly try to get the length. You can measure it with a ruler, but roughly that length. Vector w, I mean, I guess I made them different colors. Sorry, one was blue and one was brown. So let's just go back to the last one that was brown. And I'm drawing in oh, vector v first. So let's do a different color. Let's do that one in orange. So vector v is starting from head to tail method, from the head here, and it's going diagonally kind of down right a little bit. Try to get the angle the same roughly, let's say there. Again, you can use a protractor, and then going back to the brown for my vector w is going again in the opposite direction. So it's starting at the head of the second vector and going this way, but not as far over as where the first vector started. Actually, that even looks too long. It's more like that. Again, for some reason, it's hard to make those horizontal, sorry. And what is the resultant vector? What are the rules for that? I start at the beginning. So don't let it throw you off that there's 3, right? Just start at the beginning of your first vector, the tail, right here. And I'm ending up at the head or the ending point of my last vector. So I'm just simply going from here, using a ruler and doing a straight line to there and making sure that that's my head, putting an arrow on the end. And that's my resultant of adding 3 vectors together. Right there. Okay, so not too bad, I don't think. Let's look at number 2, which is where I was saying that there's also an example of where we would use the head to tail method. If I have A, B, C, D, E, F, so let's label that first as a regular hexagon. So let's try to remember what regular means, a regular hexagon. So if I have here, a regular hexagon would mean, let's label our A, B, C first. So let's say this is A, point B, C, D, going clockwise, E and F. There we go. A, B, C, D, E, F. It's a regular hexagon. That means, again, the length of AB, right, is equal to the length of BC. You probably did this in grade 9 EQAO, is equal to the length of CD, and so on. All the sides of the hexagon are the same. All the inside angles, all the angles are the same. And then we have our center point, origin O, which I can just put O, let's say right here. Let the vector AB, so now I have a vector, so let's draw in that vector. Kind of want it to stand out there. So I've got vector, now be careful, the tail is at A, it has to go in this direction. So vector AB, just try, it's supposed to be right on top of that black line there. Again, it's hard to do on the tablet, so you can see there, not bad. Vector AB is equal to, we're gonna call it vector X, so let's just label that vector X now. So I've got an X here, this is my X vector from A to B. And then I've got from B to C is gonna be just called vector Y. We're just calling it something else. You'll see why in a second. Let's do that purple. Vector. So vector, sorry, B is my tail, C is my head. There we are. And that is called vector W, or Y now. Vector Y, long day. Express each vector in terms of X and Y. That's all. So just when I'm starting at the tail of E and ending at the head of D, and I'm looking at vector ED, I'm just going to look at the exact same vector, but just change it in terms of X and Y. That is the only difference. So where is vector E to D? And let's take a look at that. I'm going to try not to use red just because red's always the resultant. I'm just trying to use, let's do blue then. So vector E to D, right here, a vector just showing in blue, E to D is, again, it does matter that E is the tail. So I'm starting at E and ending at D. So the head is at D. Okay, so there's my vector. What else can I call that in terms of X and Y is what that's asking me to do. So that would be equal to, hopefully you can see here, this doesn't really look like y, but it's exactly the same as x, right? A to b and e to d are equivalent in length. So I can just call this vector x, right? They're the same, equivalent vectors. Okay, let's try a different color here. Let's try C to D. I'm actually just going to erase just so it doesn't get too cluttered, because doing all 4 of these, right, I'll have a whole bunch of different colors there. So just to help out with that, let's try pink is not anywhere there. Oh, there we go. So C to D vector is going to be pink. So again, the tail is at C, and I'm ending at D. And now, this one is a bit more difficult than A, right? Because I'm not, with E to D vector, it was exactly the same as the green or the purple, as vector X or vector Y. Pink, my C to D vector is not the same as any of them. So I'm just gonna kind of try to emulate like your thought process here, right? Okay, so this isn't vector X. It's not the opposite, just double check, of vector X. This is not vector Y, and it's not the opposite, just showing, right? It's not the opposite of vector Y, right? That's not happening either. And then rotating that, we don't know how to do anything like that. So then the other option is, when you're kind of getting stuck here, is to look at, what else do I know? I know the resultant. So let's look at if I can get 2 other sides, if I can get this pink C to D vector to be the resultant, to be the actual answer of what 2 other vectors being added together. So let's treat C to D as the resultant. And I can get that from adding vectors C to O, and I'll show you here once I draw it. So C to O, now it is in that direction on purpose, I'll explain why. And vectors O then to D. So again, we're doing head to tail method here, because here's our head. We're doing the second vector tail lined up with the head and ending at D. And again, that, let's say, could be in red as my resultant, right? If you wanted to highlight that in a different color. But the reason being is, in order to do the tail to tail method I was saying, I would be drawing a parallelogram. Well, I already have a shape going on here. So if I just did the head to tail method, right? If I'm starting here, tail to head, and then from there, tail to head, then my resultant again has to start from the beginning of the first vector to the end of the second vector, right? So it has to go in that direction. So in that direction, I just have to watch the directions of the vectors that I put in so that the resultant answer works out according to what the rules need to be, right? So now if I look at that, that's the resultant vector is adding this vector and adding this vector. So if I'm adding this vector, C to O, so let's just say I'm adding vector C, again, watch the direction, to O to D, right? So that's going to be equal to, but now I need to refer to it in terms of X and Y. So CO, if you notice that, that's the opposite of X. So that would just be the negative X vector, the opposite of vector X. And I'm going to add that, right, to, well, that's exactly vector Y. So let's just take a look at this again. If I have the opposite of vector X going in the opposite direction, but the length is the same there, and I'm adding it to vector Y, when you add 2 things, you get the resultant. You're going to get vector C to D. So that does make sense. Okay, 2 more to do here. If I go to, I'm going to try to not move this, because I can do the answer to this kind of over here and the answer to this over here. And again, let's erase all the pink because we have too much going on here. And let's do, we've got orange, we've got green, we've got purple. Let's do this kind of burgundy maroon. I think it comes up as kind of a brownish color for you guys. So let's look at just showing here vector C to F, what's going on. So starting at the tail of C and going all the way to F. So we're just going all the way across. Oh, sorry, I thought that was in vector mode. Arrows there, starting at C and going to F. All right. Right, so the direction matters from C to F. How would I write that out in terms of X and Y? Are you noticing anything there right away? It's actually not as much work as B, if that helps you. I don't see any relation to Y right away, the purple, but if I relate this to X, I mean, this is horizontal and this is horizontal. It's just that it's going in an opposite direction. So that would be the negative vector X, but obviously my magnitude, my length is not the same. So how could I write this out, right? One of these here, the length would be equal to one of these here, C to O. One of these here, A to B, or vector X would be equal to one of these here from O to F. So I've got this as twice the length of vector X, or going from A to B. But I'm also going in the opposite direction. So that would be equal to the negative opposite X vector adding another opposite X vector, the opposite of vector X, which these are like terms. It'd be like negative 1x plus negative 1x would be negative 2 X vectors. Or in other words, I've got the X vector and I'm twice as long as my original X vector, and negative is telling me I'm going in the opposite direction, right? That one I don't think is too bad. You let me know. So now if we eliminate our color, I don't want to pick red. There's no, let's just go black, right? I don't do black too much. So now let's go from vector F, vector FD. So starting at F, now this one's a little difficult. I am going to definitely use the straight line here. F to D, nowhere along there at all, nowhere following along the lines of the hexagon there. Now that doesn't look parallel to vector X. It hopefully to you doesn't look parallel to vector Y, right? Y is steeper, as you can see. So how am I going to do this? So again, what I said was, when you're kind of getting stuck, it's not going in the opposite direction, you don't see any real link with vector X or Y, then the next thing that comes in your head is, okay, so let's look at a resultant. So if this was a resultant, I would have to be going then from, let me just get my arrow, from F to E. Again, we'll go over why, the reason why in a second, and then from E to D to get that resultant. Because again, when I draw my resultant, it's going to be from the beginning of the first vector, the tail, right, to the end or the head of the second vector. So that makes sense. That's still following along starting at F to D. And if this was a resultant, then I just have to add these two. So again, if I was adding, so D, if I was adding vector FE, right, with vector, again, order matters, F to E and then E to D, can I state that? Does that help me state? Can I state that in terms of X and Y? So F to E is in the same direction as Y. And if they're both the outside sides of the hexagon, they would be parallel. So that would just be vector Y. And adding that to vector ED. E to D was in the same direction, same length as vector X. That's literally it. So it's not as bad as we think. Vector Y plus vector X. Now, up to you. I'm totally fine with you leaving it in that order, just so you know. Or if you wanted to do it in alpha order, right? Putting the alphabetically X's first, vector X plus vector Y. I mean, that's fine. But again, to me, it doesn't really matter which order you leave it in. Just also checking it with the back of the book or worksheet. That might make a difference if you're quickly checking your answers. Just be careful of that.